Okay, hello everybody. I'm happy to see as many of you still here, and sorry about dinner last night, but it's better to eat. And I'm going to give you the sort of deep historical background in a very compressed form. And we're here partly. Originally, when I thank Murat for bringing me here at the very beginning, actually before this conference started, and the idea was to try and do non-von Neumann computing, but actually what we're doing von Neumann computing because he saw all this very clearly at the beginning that this is the way it would go. It's just the problem was that Andy Grove took us on this enormous sort of detour by building such reliable chips that we didn't have to change the architecture. I first met Andy, I don't know how old I was, but in 1991, and I was just my sister Esther's kid brother, but he was always of all the CEOs, he was kind and warm and intellectual, and we owe him a huge amount. There he's trying out one of the early Wacom tablets. So there's a long, rich history of neuromorphic. Computing's been neuromorphic from the very beginning, and we keep sort of reinventing it. That's my favorite conference logo. And Stan Ulam, who's one of my heroes, he sort of warned us that if you persist in ignoring your past, you'll be condemned to repeat it at a high cost that will be borne by the taxpayers. And of course, now that's in 1985. You update that, you would just say and the shareholders. So Stan had also a lot of input into von Neumann's ideas about neuromorphic computing. The grandfather of it all was Leibniz, who gave us the sort of rigorous digital arithmetic. And even Leibniz, when he first envisioned computing, he produced this marvelous vision that's in Latin. And what he's describing is a shift register. He's describing marbles running down tracks, and if you move the tracks, you can perform all the functions of binary arithmetic. And he illustrated those algorithms. And that's all that the von Neumann group really did, was they reinvented the shift register, except instead of gravity, they used a voltage gradient, and instead of marbles, pulses of electrons. And that's, of course, what Intel does here. They just build lots and lots and lots of shift registers. But even at the beginning of the shift register, the engineer actually doing it was Julian Bigelow, who said that von Neumann saw this as he wanted to go further than the shift register. Immediately saw that what could you do with arrays of communicating cells. And we remember the von Neumann architecture, but von Neumann only has one patent. He only patented one idea, and it wasn't the von Neumann computer. It was this subharmonic oscillator, which was really neuromorphic computing. So in his patent application, he envisions arrays of these things. They're actually 3-input subharmonic oscillators, and you can do a lot of stuff we discussed the last 2 days. He envisioned doing with it, and then of course the patent went to IBM, and they did nothing with it. He brought us the classical von Neumann machine. He didn't build the machine. What he did was he attracted the group of people who built the machine. And he had all the, why is it all von Neumann? It's because he just was the right guy in the right place at the right time with the right background. He was a precocious young mathematician. He grew up in a wealthy banking family, so he had no shyness about asking for money, and that's partly what put him so far ahead of all the other poor groups sort of struggling to keep up. He loved the military, and they loved him, so he was funded generously by the government, like Murat, what brings us here, that the it was the labs at Los Alamos that produced stuff, and he was Hungarian. He was part of, so he actually only came to America just 25 years before Andy Grove. This is Princeton in the 1930s. They're all Hungarians except for H.P. Robertson from here in Washington State. And one of his graduate students was Alan Turing. So remember that Alan Turing came to America, and a lot of these ideas actually came from Turing through von Neumann. Turing was working then, now he's trying to get his PhD on systems of logic based on ordinals, which was also non-Turing computing. These were non-deterministic machines that can do what Hava called super Turing computation. And a lot of that filtered into von Neumann's ideas. He's trying to trying to do essentially not artificial intelligence, but artificial intuition. Still a very deep subject, deserves to be followed up. Then the war came along, so Turing went back to Britain to work on the British side, doing the decryption of the German U-boat signals, and von Neumann went to Los Alamos. So the path of computing that was together in Princeton, it diverged into these two very different lineages. At Los Alamos, von Neumann worked with Dick Feynman, who ran the punch card machines, and Stan Ulam sort of stood back and had a good idea about everything. And Nick Metropolis, who ran the computing department at the lab. And they all felt that when the war was over, that actually the computing was the next big exciting thing, but there were really only two computers in the world. There was Colossus, there were actually 10 Colossuses in England, who Stephen Knowles told us about, and whose chip is named after. And in America, we had the ENIAC. And the ENIAC was also ahead of its time. It was a 20-core processor. So the architecture that Intel went to much later, they started at the beginning, it actually had 20 cores doing parallel computations. They did all the early Monte Carlo algorithms were run on the ENIAC, but run in a very clumsy, sort of improvised way. Most of that coding was done by Clary von Neumann. And then the ENIAC moved to Aberdeen. It was sort of awkward to get to. Von Neumann, he wanted his own machine to be able to play with in his spare time. He co-authored this paper that was sort of the blueprint for the next generation of computing, the EDVAC. And again, it all starts with neural principles. He uses the McCulloch-Pitts notation. And so it's all done in neural symbolism. And then showing how those neural networks can be translated into binary arithmetic, just like Leibniz did. All this had to be, it was invented out of sort of nothing. And then the classic von Neumann architecture with the memory and the input and the output. But at the beginning, he saw something much more, this was a specific case of a much more general time of computing. He was at that time already consulting for IBM. The sort of odd thing of history is, why didn't IBM build that machine for him? For some reason, he did not build it with IBM. He built it on his own at the Institute for Advanced Study, where he was completely independent. It was originally conceived by Oswald Veblen and put together by Abraham Flexner, who believed let people do whatever they want. They had their first meetings at RCA headquarters. In the group is John Tukey, who got tired of saying binary digit, so let's call it a bit, and Vladimir Zworykin from RCA. And in that first meeting, the statement was made, words coding the orders are handled in the memory just like numbers. So that's the sort of breaking of the distinction between numbers that mean things and numbers that do things. And where can they work? The whole building is full. It's right after the war. The only space is a small, almost a closet next to Kurt Gödel's office for a secretary that he didn't want a secretary. So they started in there in room 211. And Akervo, who's the last, she was 16 years old when she started working for them, somebody had to type all the documents sort of outlining this architecture, including, there's Arthur Burks and Herman Goldstein. Somebody had to manage the project. None of these projects happen without someone who actually keeps the whole team together. In this case, it was Bernetta Miller, who was the 5th woman in the United States to get a pilot's license, and then had trouble with her eyes, so she ended up running the computer project. That's their first 5 months budget, $9,348, and the first $4 for electrical work. That's the beginning of the sort of von Neumann computing industry. They were supposed to do no engineering. It was a great opposition to this engineers coming in, and that $4 was I think, to buy the plug to plug into the wall so they could plug in their oscilloscopes. The chief engineer was Julian Bigelow from MIT, a true engineer and a true computer scientist, and among his tools was von Neumann gave him Alan Turing's paper and let the whole world consist of a long paper tape. We're going to build Turing's linear abstract machine, but we're going to give it a two-dimensional memory. And the odd thing is that here we still are all these years later, and we still mostly run on just a strictly two-dimensional memory. So that's their copy of the Proceedings of the London Mathematical Society. There's been a lot of debate. Did von Neumann, acknowledge Turing or not? Of course. And the copy of Turing's paper is disbound because it was consulted so much by the engineers. So Bigelow has a lot to say to us because he was the closest collaborator with von Neumann and can tell us what von Neumann was thinking at the time. He also explained that the MANIAC was a mathematical numerical integrator and computer. It was asynchronous. It didn't have a clock speed. It just went through an instruction and went to the next at whatever speed you wanted. You could actually run it step by step. You don't need clocks. There's a difference between a clock and a counter. Sequence is different from time. No time is there. And that's very profound. We got away from that with the strictly clocked microprocessors, but I'm so happy to see so many of you are going back to looking at asynchronous systems that can be powerful in different ways. Vladimir Zworykin came in from RCA, who was doing a crazy project. This vacuum tube called the selectron was effectively an integrated circuit within a vacuum tube. It was like if we hadn't had the Andy Grove integrated circuits, we might have ended up with a world full of these giant vacuum tubes that were 4,000-bit integrated circuit memories within a single glass envelope. So all this, the big picture is that we had all this analog equipment after World War II, and we put it together to build digital computers. And I think what's happening now in the world that we have all this digital equipment and we're starting to build analog computers, even though we don't necessarily acknowledge that. If you look on the internet, a lot of the computation is really being done as continuous functions on continuous variables. And the complexity is in the topology, not the code. So that's the first shift register, the realization of Leibniz's everything was done with a 6J6 tube. It was the cheapest, most inexpensive tube. Bigelow believed it would be most reliable, which was true. And that's why you want to use the components that are made in the largest numbers. But they had no selectrons. What could they use for memory? This was a magnetic wire on two bicycle wheels that they could get 90,000 bits per second input-output onto that. It was effectively a hard disk. Then in England, they heard about Thomas Kilburn and Freddie Williams, who were doing, and this is Manchester, so this is the ancestor of the Spinnaker lab. It's sort of a direct ancestor. Storing bits as charged spots on the face of cathode ray tubes. So that became the working memory with 1,000 bits in each of those tubes. So that's the dawn of the digital universe where the pixels are not representations of bits. The bits actually are pixels on a charged glass space. So it's a touch screen in reverse. Oppenheimer was the director, very supportive. The main project, of course, was funded to do weapons design. It was very successful, but the deal was if they designed the weapons, they could do whatever they want with a computer the rest of the time. So von Neumann did all sorts of crazy things, including trying to evolve digital numerical organisms to let them evolve in the memory space, which was only 5 kilobytes. And that was remarkably successful for the time. And Bigelow said that Baricelli, who did this, was the only person who really understood the path toward genuine artificial intelligence, that it would have to be allowed to evolve. It would not be programmed. So when I went digging around, I found one of Baricelli's universes in a box in the basement of a building and a note from the engineer. There must be something about this code that you haven't explained yet. And that's really what brought Turing into the whole thing. The whole thing that brought Turing into computing was the Scheidung's problem, the decision problem. Is there any systematic way looking at a string of code to tell whether it's a provable formula or not? There is no way. So there's no, even a very simple code, you can't tell what it's going to do except by running it. Tragically, Alan Turing dies in 1954. Von Neumann dies in 1957, both way too young. The machine gets shut down. That's Midnight Bigelow running the last problem. So it's Julian who lived longer, and even though he was very bitter about what happened, he gave us some glimpse into what they were really thinking about. This was just the first computer. If you brought Turing and von Neumann and Bigelow back today, they would be just astonished that we're still just mostly doing what they did, but faster, and except for this group. So they've been waiting for you for a long time. Why do we build all these very fast gates and switches and then only use one of them at a time? So all this is nothing. This is preaching to the converted. You know all this, that there's totally different ways of running information through a computer than by just serially programming it. And part of this was driven by that machines are so fast that they eat up instructions faster than people can write instructions. So the programmers have to do these iterative processes that can generate long sequences of instructions. But nature will throw information at you directly in all sorts of ways. And the chips that are coming online now will be able to do that. So it's very exciting. The last thing von Neumann sort of published after his death, but wrote before his death, was his book on the computer and the brain, which was not what people think, that the brain and the computer were similar, but why were they so different? And why was the brain reliable and why were computers unreliable? And von Neumann was very clear that there's no way, the only way to really describe a visual analogy is the connections in the, what you're doing. This goes way back to people like Alfred Smee, who he's trying to define consciousness. It's the ability to tell the difference between reality and thought, and how does it happen. He was looking at deep, what we would now call neural networks. Wanted to build a machine that would do this. Would be like a search engine, would be like a layered network, a semantic network, but what he didn't have was electronics. Electronics was brought to us by John Ambrose Fleming, looking at the problem of Edison lamp bulbs. Why was there light was going in all directions, but there were particles that were going only in one direction. And that's how we found out about electrons and how we developed the first, in fact, semiconductors, and then Lee DeForest put a third electrode in that became the grid. Suddenly we had control, and we had machines that could operate at the speed of light, not the speed of sound. And Fleming was an anti-Darwinist, believed that the universe itself had a mind of its own. And I think that's an important idea, that in AI, you're not so much building intelligence, you're building something that can enable the mind of the universe to manifest itself. And another strong believer in that was Louis I. Richardson. Everything you need to know about AI is on this slide. This is an electrical model illustrating a mind having a will, but capable of only two ideas. So it's a non-deterministic circuit that has quantum free will, but only has two ideas. But you can scale, you guys are good at scale. You can scale that up and build very interesting non-deterministic machines. Ross Ashby thought about this, so I'm going to give you three laws of AI that are sort of my own three. Ashby's law of requisite variety, that any control system has to be as complex as the system it controls, which has good and bad results. Von Neumann's law, which is a complex system, constitutes its own simplest behavioral description. As soon as you try and describe it in a logical way, it gets more complicated. You find that with the neural network of a flatworm is cannot be described except the network is the most compact description. And the third law doesn't have a name. Any system complicated enough to behave intelligently will be too complicated to understand. And that has always given people a sense of safety. We don't need to worry about AI because we can't build it. It's too complicated. But there's a loophole in the third law, and you guys are all working in that space. It's entirely possible to build something without understanding it. And many good people have thought about this. One of my heroes is Oliver Selfridge, who developed an early sort of deep learning program called Pandemonium, which does pattern recognition problems by again, weighted networks, and then allows the optimum solutions to replicate machine images of themselves, and it evolves. And of course, Jack Good, who was sort of, Ulam was von Neumann's closest colleague, and Jack Good was Turing's closest colleague, and they worked together doing the decryption during the war. So this is really the laundered version of everything that was secret in World War II. How did they break the German codes? And they did it. This is really a book about Bayesian inference networks, and well worth rereading. Jack Good also voicing Turing that you want to start with a completely random network because then it contains all the random, you don't have to specify in advance. It has all, which is how we build brains. They contain every network you might ever need. And it was Jack Good who talked about ultra-intelligent machines, which basically, a machine, his definition, that's a machine that thinks people cannot think. And he also wrote about ethical machines. This paper has never been fully published. The published version left out all the good stuff, just published the boring stuff. So get the unpublished version. Answers all the questions about the critics of, who worry about AI without ethics. And then machine consciousness, Jack Good asked Turing, when would a machine be conscious? He replied he'd say so if he would otherwise be punished. And now we're back to von Neumann. So von Neumann and Ulam were going to write a book together. It never got done. But this was the outline of chapter. So we have Turing, not Turing. Those are that's sort of super Turing computing. Pitts-McCulloch, what you can do with neural networks. Ulam, all sorts of clues in here of what they were really thinking about. I'm going to give the last word to Stan Ulam. He's winning at poker at Los Alamos. He's had an effortless way of solving problems and winning. What makes you so sure that mathematical logic corresponds to the way we think? It was silly to assume that, and it's definitely not true. I mean, we think logically, but the underlying processes are not logical. They're non-deterministic, stochastic, and what's exciting to me, what we're hearing about here mostly is domesticated neuromorphic computing. The neuromorphic computing that's being done on the chips and in the labs. And personally, this is just me as a sort of wildlife biologist. I'm interested in neuromorphic computing in the wild, sort of what's happening in the larger sort of internet at large, where we're starting to treat more and more of our large operations like Google or Facebook or something are treating streams of bits the way vacuum tubes treat streams of electrons. And that's back to the main message is that I think we're building analog systems on top of the digital the same way we built the digital on top of the analog. And doing it on the chip is one step forward. Thank you to all the people who let me into their basements. If you send me an email at IAS and it's just one line of text, that'll take about 10 times the memory that they did all that work with 60, 70 years ago. Thank you. I don't know if we have, if there are any questions, I'll answer questions, but is there any questions?
When does the movie come out?
I don't know. It baffles me that, it's a good sign that movies like Hidden Figures have done very well. In fact, I'm consultant on a film about Ulam and von Neumann being done in Europe. So I think there's hope because it's such a great story. And it's, we get all the Steve Jobs sort of mythology, but this, and there were so many women involved who were characters. And so I think it's a great film. So all I can say is I'm happy that a film is mostly about Ulam and von Neumann in their sort of weapons work, but still that this, suddenly movies about mathematicians are getting funded, and that's overdue. Great.
Just because I'm from Los Alamos, I have to ask this question. So bomb making was a big motivation for the initial computer, for the ENIAC. And then for many years, well, including now, the lab just buys commodity off-the-shelf hardware that it, puts together into very large machines. But going forward, I wonder if you think that that kind of activity can motivate new kinds of computer architectures still.
Yes, very much. I think I'm not behind the scenes, but I think a big driver of neuromorphic computing is drones that need very efficient pattern recognition and things like that. The drivers are still often come from, and ARPA, is the ancestor of ARPA was the Office of Naval Research, and they're still here funding a lot of the most interesting stuff. So I think it was the deal was made that the lab funded the computer, the AEC funded the computer, and they wouldn't tell the scientists what to do with the computer. The scientists could do whatever they wanted with that computer, and they did the craziest stuff. But the other part of that deal was that the scientists were not supposed to tell the government what to do with the weapons, and that's where Oppenheimer got in trouble. He broke that deal. He started telling the government what they should do with their weapons, and that's why he got crucified. I think so I think as long as you stick to that deal, it's a very fruitful deal, and some of the greatest, the origins of information biology, and all that came out of the labs because there was the freedom to play around. So I think we'll stop there and try and catch up on time, on schedule.
I ask one more question, sorry.
quick.
I don't know if the take-home message for me from your talk is make the usefulness with the useless knowledge. Can you comment on that?
Well, it worked, but it kind of only worked once. I mean, that was the grand dream of Flexner, was let people come to this institute and work on whatever they want to, and the computer was really the only big thing that came out of that, and that was just by accident. It was a historical accident that when I was going to do it at RCA, and then the Navy decided they couldn't fund RCA because that would be a conflict of interest, and so I think that's why it happened at the institute. But nothing else ever happened. They had a wonderful celebration there for Einstein's 75th, or for the institute's 75th birthday, and Jim Wolfenson, who director of the World Bank, gave a great, lubricated after-dinner speech, and he said, if we come back in another 75 years, I hope you have something else to celebrate besides Einstein. And it's true. It's just that it's very hard we know how hard it is to get creative things to happen. What makes that spark? I don't know.
Okay. Thank you.
Good question. Thank you.